laser radiates produce cognizant signs all through the world. Furthermore, we, as people, are not, sadly, sufficiently shrewd to grasp them. Andromeda, our cosmic neighbor, can be seen in our skies without a telescope, which is fascinating. Anyway, things have gone from intriguing to upsetting and disturbing. Michio Kaku has uncovered that the James Webb Space Telescope has gotten upsetting signals coming from Andromeda, and these signals end up being significantly more perilous than ever expected. Join us on this excursion to find the truth behind these disturbing signs and how the future could undeniably be more unnerving than we at any point imagined. Andromeda is a huge Goliath with interesting qualities that recognize it in the vast universe. Otherwise called M31, or more chaotic 31, it is the largest universe in our district with a great width of roughly 220,000 light-years, a genuine heavenly miracle in terms of its astronomical size. Albeit the Andromeda system lies at a significant distance from Earth, roughly 2.5 million light-years away, its position in the universe places it past the restriction of our cosmic area, the Andromeda Galaxy's structure. Despite the fact that its size might be terrifying, it is also entrancing to notice its structure. Andromeda shares a comparable foundational layout to our own Milky Way galaxy, with a barred spiral setup. This element is featured by a central lump of matter, encompassing a flat disk containing stars, gas, and enormous dust. Its balanced structure shows the amazing intricacy of this universe in terms of its heavenly population. Andromeda is home to an exceptional 1 trillion stars, far surpassing the quantity of stars in our own Milky Way galaxy, which has around 250 billion stars. This makes sense of why it is so noticeable from Earth, since its splendor is certainly greater. However, loftiness and radiance are not the only fascinating qualities it has. Open space conceals numerous mysteries, and every universe has unique and astonishing quirks. At the center of the Andromeda system, a concentrated lump of matter hangs out in the twisting structure of the world, enlightening a clear appearance. The central lump is believed to contain a high concentration of stars, affected by the gravitational pull of the actual universe. Considering that the universe has an overflow of stars, it is no surprise that a portion of them bunch together to form this lump. Furthermore, there are more than 400 globular clusters dispersed throughout the Andromeda Galaxy, which are circular assortments of stars bound together by gravity. Andromeda's satellite galaxies. Despite being an enormous cosmic monster, the Andromeda system is not alone in space. In fact, it has an escort of at least 14 known satellite systems circling around it, forming an interesting grandiose family. The interactions between the primary galaxy and its satellites play an important role in the development of their respective structures and advancement, adding to the rich variety of enormous peculiarities in the Andromeda framework. The presence of a ring of dwarf galaxies surrounding Andromeda has been discovered. These dwarf galaxies are generally small and faint compared to Andromeda and the Milky Way. The discovery of this ring suggests a gravitational connection between Andromeda and these smaller galaxies, showing that the dwarf galaxies are under the gravitational influence of Andromeda, likely due to the immense gravitational power of this galaxy. The ring of dwarf galaxies is a subject of active research, as the exact nature of this interaction and the mechanisms that led to the formation of this ring are still under study and investigation by researchers to advance our understanding of galaxies, dark energy, and star formation, including the Andromeda Galaxy. Two powerful instruments are being used to study the Andromeda Galaxy and its surrounding cosmic environment: the James Webb Space Telescope, JWST, and the Dark Energy Spectroscopic Instrument, DESI. These instruments play a vital role in the study and examination of enormous peculiarities, allowing the mysteries surrounding the Andromeda Galaxy and its heavenly climate to be examined more meticulously and accurately. The James Webb Space Telescope is considered the most powerful telescope ever built and is designed primarily to observe the universe in the infrared range of the electromagnetic spectrum. This feature allows it to concentrate on the first galaxies forming in the early universe by detecting the weak light emitted by these distant galaxies. The James Webb Space Telescope will likely provide significant insights into the formation and development of galaxies, including Andromeda, and its observations will contribute to our understanding of the processes that have shaped the universe over time. On the other hand, the Dark Energy Spectroscopic Instrument, DESI, is an instrument specifically designed to study dark energy and galaxies. DESI uses optical spectroscopy, which involves breaking galaxy light into its various frequencies to examine the spectra of millions of galaxies. Through this massive spectroscopic survey, astronomers can measure the distances to galaxies and obtain information about their properties, such as their chemical composition, evolutionary history, and motion. DESI's investigation of the distribution and movement of galaxies offers insight into the mysterious nature of dark energy, a mysterious force that drives the accelerating expansion of the universe. In the specific context of the Andromeda Galaxy, DESI observations have provided captivating insights into the stellar population of stars within it. By investigating the spectra of individual stars, DESI can reveal information about their chemical composition and origins. This allows astronomers to track the history of star formation and follow the evolution of stars within Andromeda. By learning more about stellar migration patterns, researchers gain a better understanding of the formation and development of the galaxy, as well as its interactions with neighboring galaxies. Additionally, recent studies have provided definitive evidence for the presence of a stellar corona in the Andromeda Galaxy that bears similarities to that of our own Milky Way galaxy. This discovery has illuminated the dynamic nature of galaxies and the complex interactions between them. Observations and simulations suggest that a large number of stars observed in the outer regions of Andromeda's stellar corona have migrated from smaller satellite galaxies that were gravitationally captured by Andromeda over time. Some dwarf galaxies merged with the Andromeda system, taking their stellar populations with them. This process of cosmic barbarism is known as galactic accretion or merger. Galactic mergers are believed to be common in the universe and shape the structures and characteristics of galaxies, including Andromeda. The presence of stars from other galaxies resulting from interactions and mergers with smaller companion galaxies helps astronomers understand the kinematics and distribution of stars in the stellar coronas of galaxies like Andromeda and the Milky Way. By studying the populations of stars in these star coronas, astronomers can trace the history of galactic mergers and interactions that have shaped these galaxies over billions of years. The stellar corona contains stars that have been stripped away from smaller satellite galaxies or star clusters, and their properties can provide valuable information about the history of galactic mergers and accretion. This process has been a critical factor in the development and arrangement of galaxies like Andromeda and has contributed to the diversity of features and structures observed in them. Through detailed observations and simulations, researchers can analyze the chemical composition, age, and movement of the stars that form the stellar coronas. This data allows them to recreate the timeline of galactic mergers, identify the progenitor galaxies that contributed to stellar populations, and understand the physical processes involved in such mergers. This approach is of utmost importance because, if this vast galaxy were ever to come into contact with our own, it would be essential to be prepared with all available information. The study of galaxies extends far beyond simply understanding their physical attributes and interactions. It delves into fundamental questions about the origins, structure, and fate of the universe itself. One of the major areas of interest is the role of galaxies in cosmic evolution. Galaxies are the building blocks of the universe, each serving as a laboratory for the study of star formation, black hole growth, and dark matter. Their formation and evolution can offer clues to the early states of the universe and the processes that have shaped its large-scale structure. Galaxies are not static entities. They are dynamic systems that evolve over time. This evolution is driven by various processes, including mergers, interactions with other galaxies, and internal dynamics. The study of galactic mergers is especially important, as these events can trigger bursts of star formation, impact the growth of supermassive black holes, and reshape the structure of galaxies. The Milky Way itself has undergone several mergers throughout its history, and understanding these events helps researchers model its future interactions, including its impending collision with the Andromeda Galaxy. Recent research has also focused on the role of dark matter in cosmic evolution. Dark matter, an invisible form of matter that does not emit light or energy, makes up a significant portion of the universe's mass. Its presence influences the structure and dynamics of galaxies, affecting their formation and evolution. Observations suggest that dark matter forms a halo around galaxies, affecting the rotation curves of galaxies and the distribution of visible matter. By studying the interaction between dark matter and visible matter in galaxies, astronomers hope to better understand the nature of dark matter and its role in cosmic structure formation. Another key area of cosmic research is the study of galactic feedback mechanisms. Feedback from star formation and supernova explosions can significantly impact the surrounding interstellar medium, influencing subsequent star formation and galaxy evolution. This process is essential to understanding how galaxies manage their own evolution and maintain their observed properties. High-resolution simulations and observations of neighboring galaxies are helping to unravel the complexities of these feedback mechanisms, offering insights into how galaxies recycle gas and elements over time. The study of active galactic nuclei, AGN, is another fascinating area of research. AGNs are regions at the centers of certain galaxies where a supermassive black hole is actively accreting material. The intense radiation and outflows from AGNs can influence the surrounding galaxy, impacting star formation and the overall cosmic environment. By studying AGNs, astronomers gain insights into the growth of supermassive black holes and their impact on galaxy evolution. Observations of distant AGNs offer a window into the conditions of the early universe, helping researchers understand the formation and evolution of galaxies in their infancy. The role of galaxies in the larger cosmic web is also a point of great interest. The universe is structured in a vast network of filaments and voids, with galaxies and galaxy clusters forming along these filaments. Understanding the distribution of galaxies within this cosmic web helps researchers study the large-scale structure of the universe and the influence of dark matter and dark energy on cosmic expansion. Large surveys such as the Sloan Digital Sky Survey, SDSS, and the upcoming 3D mapping projects aim to map the distribution of galaxies and explore their role in the grand cosmic web in greater detail. The study of galaxy clusters also provides important information about the large-scale structure of the universe. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies. They are essential for understanding the distribution of dark matter and the impact of dark energy on cosmic expansion. Observations of galaxy clusters help scientists measure the properties of dark matter, determine the rate of cosmic expansion, and study the formation of large-scale structures. In summary, the study of galaxies encompasses a wide range of scientific inquiries, from their formation and evolution to their role in the cosmic web. By examining the physical properties, interactions, and feedback mechanisms of galaxies, astronomers gain significant insights into the fundamental processes that shape the universe. The integration of observational data, theoretical models, and cutting-edge technology continues to drive progress in our understanding of galaxies and their influence on the larger universe. As we advance our observational capabilities and refine our theoretical models, we inch closer to unraveling the mysteries of the universe and our place within it.